All right, PreCalc, this is it, 10.7 probability, the last section in chapter 10. All right, so we're going to compute first empirical probability, which means we're actually going to use real data. So the number of times something is observed over the total number of times it was observed. So total over on the bottom, and then how many times it was observed on top. So empirical is real life, things we have. So in this case, we have a chart here, the marital status of United States population ages 18 or older in millions. And the data they collected were from males and females, if they've never been married, if they've been married, if they've been widowed, if they divorced, and the total number that they found. So in this case, they are keeping track of so there's 102.4 million that were surveyed. For males, there were 110.1 million females that were surveyed, and they fit in one of those categories, okay? And then it gives us the total of everything. So for number one here, if one person is randomly selected from the population described in the table, find the probability to the nearest hundredth. And by the way, a lot of our probability we will turn into decimals because it makes more sense, or more specifically, we later change them to percents, that a person is divorced. So we want to know how many people are divorced. And so if we look here, because we're not narrowing it down between male and female, we're going to go for the total number of divorced, which is 21.7, over all of them that were surveyed total. So again, we're using this total number of 212.5. Now remember, they told us everything's in millions, but because everything's in millions, we can leave them just like that, divide through. So we're just looking at the occurrences of 21.7 on top divided by the total number surveyed, and we get 0.10, I wouldn't even round that, 0.102, so I leave it 0.1. And if you think about it, if you turned it into a percent, it'd be about 10%. All right, for the second one, among adult women, so we are narrowing it down here, find the probability of selecting a married person. So we want to go to our women, we want to find our married number, so 62.8 were married. And then my total here, because I'm selecting among women, I only want the women total number, which is about 110.1. And again, top divided by bottom, if that's how you want to think about it. And we get about 0.57 to the nearest hundredth here, or about 57% of the adult women that were surveyed were married, okay? That's empirical, using real data, okay? We do a lot of probability, however, with theoretical, over when we're talking about, here's the number of outcomes in the sample space of whatever we're looking at, and then this is the number of times it should be able to occur. So this is a slightly different than what might have occurred in real life, but this is what we have. These are the likelihoods, okay? So for number 3, we have a die is rolled. Find the probability of getting a number less than 4. Well, when I roll a normal die, there's 6 rolls I can get. So that's going to be my total on the bottom is going to be 6. Now, a number less than 4, not equal to 4, but less than 4. So I can get 1, 2, or 3. So I get 3 out of 6 choices. So I can make it 1/2, or as a decimal is 0.5, okay? And I will tell you different times if I want it to the nearest tenth or as a fraction lowest terms. A lot of times the fraction is the easier one because that's how we work with it. For number 5, you're dealt 1 card from a standard 52 card deck. Find the probability of being dealt a black jack. So we know the total number of cards are 52. How many of those cards in that deck are a black and a jack? Well, there's 2 black suits, and there's a jack in each one, so there's 2 of them that are black jacks. We reduce that to 1/26. If I decide to turn that into a decimal, I get about 0.04. So 4% chance of getting that blackjack, kind of small. All right, a state lottery is designed so that a player chooses 6 numbers from 1 to 30 on a 1 lottery ticket. What's the probability that a player with 1 lottery ticket will win? What's the probability of winning if 100 different lottery tickets are purchased? Okay, so that person has 1 ticket, so they get 1 chance out of how many? Well, how many different combinations of 6 numbers are there in a lottery ticket? And actually, I need to go back to that word I just used. How many different combinations? Because when you choose the lottery numbers, you don't have to have a certain number in the first spot or in the second spot or in the third spot or fourth spot. You just need to select a number, and they look at all the numbers you selected and say, did you get the same 6 numbers as the lottery? So that's a combination. There's 30 numbers to choose from, 1 to 30, that's 30 different numbers. And I can only have 6 numbers, so I'm using a combination of the 30 and the 6. So you can go ahead if you want, and you can do your 30 factorial over your, we do 30 minus 6, right? Minus 6 factorial times 6 factorial, right? Or if you remember that handy dandy little button on the calculator, make sure you type in 30 first, and then hit your button. Make sure you're using the combination, not the permutation one. And we get a number of like 593,775. So that's how many different combinations we have of lottery tickets if you're guessing 6 numbers from 1 to 30. All right, so when you do 1 divided by that 593,775, you have a 0. We might as well go till we get some significant digits, right? 1, 2, 3, 4, 5. 5 zeros, and then I get a 1684. Yeah, that's a pretty slight chance of winning that lottery, which I'm hoping you already knew. So what's the chance if I had 100 different tickets and they were all different? So I have 100 of those 593,775. Will that help my chances some? Well, a little bit, but if I just multiply that last answer I had by 100, all it's going to do, I'm down to 3 zeros, right? And then my 1684 and so on, right? I still think about that. It's still less than a 0.01% chance of winning, even if you buy 100 tickets. You're better to invest your money, right? Don't buy the tickets. All right, we're on to page 2. We're still going to go, this is all more theoretical probability, but we have the probability of an event not occurring. So if something is definitely going to occur, it's 100% or 1. So if it's not occurring, we're going to do 1 minus the chance that it would occur, okay? So it says when dealt one hand from a 52-card deck, find the probability you are not dealt a king, okay? So if I'm not dealt a king, I'm going to find out first what's the chance I'm dealt a king. So I have 52 cards, and 4 of them are kings, okay? So if I want the not, I'm just going to do 1 minus 4 over 52, okay? 52 over 52 minus 4 over 52, that leaves me 48 over 52. And sure, I can reduce that by 4s maybe, and I can get 12 over 13, which makes sense, right? And, you reduce, and there's 13 cards in a suit. 12 of them are not kings. We go to a decimal here, 12 divided by 13. How about 0.923, something like that, 0.92, right? There's a chance I'm not dealt a king. Okay. Then we have probabilities with mutually exclusive events or with independent events, okay, or not mutually exclusive events. So it says if A and B are mutually exclusive events, then the probability of A or B equals the probability of A plus the probability of B, okay? Or if you go back to set notation, that's my union, right? So it's saying I'm going to include everything. I get the chance of everything. So it says when dealt 1 card from a 52-card deck, find the probability you're dealt a red 5 or, and that's an important word, a black 6. So how many red 5s are in a deck? Well, there's 2 red 5s out of 52 cards. How many black 6s are there? Well, there's 2 out of 52. So if we have this or, where I'm just looking for one of the 2 to occur, I just add my probabilities together. So that's going to give me 4 out of 52, and I can reduce that to 1 over 13. I should go to the decimal on that one, and it looks like I have about a 0.077 or 7.7% chance, right, of that occurring, okay? All right, probabilities with events that are not mutually exclusive, meaning you're not going to see that or, you're going to see probably an and, okay, between them, so that I shouldn't say that they don't go together, okay? So what we're going to do is we're going to find the probability of the 2 things occurring and then subtract basically this and part, which is my overlap, okay? Because sometimes the 2 go together and there's an overlap of cards that match both, or I shouldn't always say cards, there could be other things. But this first example, when you're dealt 1 card from a 52-card deck, find the probability you are dealt a 10 or a red card. Well, when you're doing a 10 or a red card, some of my red cards are 10s, or some of my 10s are red cards, so there's that overlap. But we're going to just start. What's the probability I'm dealt a 10? Well, there's 4 10s in my 52 cards. What's the chance I'm dealt a red card? Well, half of my cards are red, so 26 out of 52. I'm going to add those together, but then I'm going to subtract how many of those overlap. So how many of my 10s are also red? Well, 2 of them are. So I'm going to take away 2 of my 52 to get my probability here that this would occur. So 4 plus 26 is 30, minus 2 is 28. So my final answer is 28 out of 52 cards to match this rule. 28 divided by 52 is 54%, right? Or about 0.54 that those two things are going to occur. Okay. And then we have independent events. If A and B are totally independent events, which means one does not matter about the other one, okay? So they have basically nothing to do with each other. They're not going to prevent the next thing from happening. It's just they happen individually from each other. So for number 9, a single die is rolled twice. Find the probability of rolling a 3 the first time and a 1 the second time. So if I have one die and I roll the first one, I'm rolling a 3. Well, there's 1 3 out of my 6 choices. The second time, I pick up the same die. It's not like because it landed on 3 the first time, it lands on something else the other time. One doesn't have anything to do with the next. So what's the chance it's going to land on a 1 the second time? Well, once again, I have a 1 in 6 chance of landing on a 1. All I need to do is multiply. It's like the counting principle. 1 over 6 times 1 over 6 is 1 over 36. They didn't have anything to do with each other, and that comes out to about 0.03. All right, last time. Find the probability of a family having 4 boys in a row. Well, you realize it's not like you get an even chance, right, when you have a kid. So I shouldn't say that. You do get an even chance. You don't have now that you've already had your boys, you're going to have your girls. That's not true. So the first boy, I get 1 out of 2 chance of having a boy. Second child, 1 out of 2 chance of having a boy. Third child, 1 out of 2 chance of having a boy. Fourth child, 1 out of 2 chance of having a boy. So every time it's 1 out of 2. There's nothing else. There's not a lean towards one way or the other. Okay, so what's the chance you're going to have 4 boys in a row? Well, 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2 is 16. So 1 in 16 chance of having 4 boys in a row. As a decimal, it's about 0.06. All right, about a 6% chance of having 4 boys in a row. Because each time you get a 50% chance. All right, that's my probability lesson, okay? That's what I have for you. That's what you can practice. It definitely is one that you might want to take that chance to practice on it, because if you're not sure when things are mutually exclusive, when they're not and such, the practice will help you work through that, okay? So homework, try page 1026 to 1027. And we're looking at 3 through 51 by 3s are good practice, or do the odds so you can look them up in the back of the book, or do the by 3s and look them up on Slater, but practice definitely would benefit you. All right, let me know if you have any questions.